Hello and welcome to Lecture 27. Here we're going to cover section 8.3 on the topic of equilibrium. Okay, so this is the first section where we're really kind of going to be putting torque to use. We've defined torque, but now we're going to be involving it in a certain type of problem, specifically a problem that involves this concept of equilibrium. But what is equilibrium? Well, equilibrium is defined as a condition of a system where the net force, so the sum of forces, is equal to zero. Notice this is the force vector, so this could be F net x equal to 0 or F net y or both, okay? And then we also want the sum of torques, in other words, the net torque to be equal to 0. Yes, it's a vector, we don't care about its direction, but it is technically a vector, okay? So that's the idea, is we have all the forces summing to 0 and all the torques summing to 0. And if you don't remember the definition of torque, review it, make sure you understand what we're talking about when I say torque. Now, equilibrium is synonymous with zero acceleration. So it's always a zero acceleration system, both zero translational acceleration and zero angular acceleration. Because notice that this obviously would be equal to ma, and then we'll see later this one would be equal to I alpha, but that will be in the next section. But for now, this is a good way to start using torque because having it equal to 0 is a simpler start than, say, having it equal to something that's not 0, right? Okay, so there's simply two types of equilibrium. Not a big difference between how you approach either of them, but conceptually they're a little bit different. There's dynamic equilibrium, so still zero acceleration, but non-zero velocity. So this is a system that's coasting at constant velocity. All right, so it's something that is moving along, maybe translating at constant velocity, spinning at a constant rate, whatever it may be. It's not slowing down or speeding up. Now the more common type of equilibrium is equilibrium with zero velocity at rest. Okay, but the approach for both is the same. Okay, it's just the different types of problems. Okay, all right. And when we actually approach equilibrium problems, this is really what we're going to be doing. It's a very mathematical, formulaic approach, as in many types of our problems. We write out a sum of torque equation, so a net torque equation. We make sure it's equal to 0, and then we write out a sum of forces in the x direction, set those equal to 0, and then do the same thing in y. And that's how we start every one of these problems. Okay. All right, and there's two types of problems. Again, not a different approach for either of them, but there's problems that involve static equilibrium, so things at rest. And what we're going to be doing with those types of problems is we're going to be calculating forces under distances. And then with the dynamic equilibrium, we're also going to be doing the same, setting up a problem, and then solving for forces under distances. Okay? Now, let's start with a really kind of typical static equilibrium problem, which involves some sort of construction, something you would see in engineering. Maybe it's like a signpost. In this case, it's a big beam being supported by some cable of some sort and someone standing on it. Okay, so there's going to be forces at play, and then there's going to be some consideration of both sum of forces and sum of torques. And what's really new, what really sets this material apart from what we've seen before, is of course that idea of torques. And since we are talking about torques, the location of forces matter because the displacement from the pivot matters. And that was something we never considered, right? We've done plenty of free body diagrams. We've seen plenty of forces that may look like the diagrams here, but it didn't matter where we drew the force vectors before. I could have, for example, looked like this vector right here. I'll zoom in a bit. This vector here represents the weight of the beam itself. Okay. Now, before, if this was a gravitational force vector, I could have really drawn it wherever I wanted. I could have drawn it over here, right? Maybe I should draw it to scale, but I could have drawn it wherever I wanted. But now it matters because now I need to know that it's 2.5 meters from the edge. And maybe that's my choice of pivot. In this case, it is, okay? That's the rotational axis, the pivot point, okay? The axle, however you want to think of it. And that's really what is new with this material. It's a new consideration. It's actually a new tool that helps us solve problems that we couldn't have solved before. Okay, let's go ahead and read this problem. So we have a uniform horizontal beam that is 5 meters long. It weighs 300 newtons. It is attached to a wall by a hinge that is free to rotate. Okay, so that's going to be our pivot point. All right, its far end is supported by a cable that makes a 53-degree angle with the horizontal as shown. Okay, that's the angle. And if a person weighing 600 newtons stands 1.5 meters from the wall, so they're closer to the wall than the center of the beam, what is the tension in the cable? And what is the force, which we call R, exerted by the wall on the beam? Okay, and R here, you can think of it standing for reaction force, obviously T for tension. Okay, so if we zoom in, then we see that we have the tension. Okay, we know the angle of the tension, so we're really interested in its magnitude. And then we can split that reaction force into two parts. There's a vertical and horizontal part. because essentially the beam would push on the wall would push back with a normal force, and then this Ry would either be a friction force or be some sort of actual mechanical support. Maybe the beam is notched into the wall, for example. Okay, but these are the two forces, whatever is causing them, that are supporting the beam both in the horizontal and vertical directions. Okay, so let's start this problem. All right, and we'll get used to the technique of solving problems like this, but this is a good one to start with. Okay, so what should we do first? Write the sum of forces and torques. Okay, and I should say one thing we should probably even do first, even before we write the sum of forces and torques, is choose our pivot. Because although that doesn't affect anything in terms of our consideration of forces, it's crucial for our consideration of torques. Because torques only make sense, and again, review torques if you don't recall this. Torques only make sense. They only have a definition relative to some pivot. I can't just say, oh, there's a 20 meter torque on that ball there. Well, is it 20 meters relative to its edge? Is it 20 meters relative to its center? You need to know, okay? All right, so there's our choice of pivot. And the only reason that I'm pointing to two places is because there's two figures. This is the pivot in the zoomed out figure, and then the one that's just focusing on the beam, that would be the pivot right there, recognized as the origin of our XY coordinate axis, okay? All right, so now we're gonna write the sum of forces and torques. Now that we basically have our free body diagram and we've chosen our pivot, we go on to write forces and torques, okay? So F net X, what are all the forces in the X direction? Well, let's take a look, right? This is a good place to look right here. Well, there's the reaction force from the wall, and then there's a component of the tension force. They have to be equal to 0. Why? Because this is an equilibrium problem. Everything's at rest. All right, and then in the Y direction, we have some more forces. We've got a component of the reaction force. We've got a component of the tension force. Okay, again, known angle. And then we've got the two weights, both down, because we have positive Y pointing up, positive X to the right, and, very important, positive theta, right? So positive angular movement in the counterclockwise direction. These would all be the typical choices. So now finally, our sum of torque equation. And this is relative to the pivot. It has to be, okay? Not that we could choose, we could have chosen a different pivot, but this was a good choice, all right? And let's then take a look, right? So relative to our chosen pivot, we've got a component of the tension force. It's only the component of the tension force that is perpendicular or tangential. I think I meant to say, I might have said tangent force. I was thinking, so let me rephrase it. It is the component of the tension force that is tangential to the displacement vector. In other words, it's T sine of 53 degrees, okay? And again, that's the whole deal, right? That when it's only the force that's perpendicular to the displacement that creates torque. Or if you think of the total force, the magnitude of the force, then it's only the component of displacement, which is known as the moment arm, that actually creates the torque, okay? But here we're really taking a component of the force, and we're considering the entire length of the beam, L. Okay, and what about the two forces from gravity? They create torques as well. All right, so we're going to have a torque from the gravitational force from the person and a torque from the gravitational force of the beam, okay? Both of those are already 90 degrees, so we don't have to worry about any angles, all right? So we have the full force times basically the moment arm, which is also the displacement, okay? And so essentially we're taking sine of 90 degrees on both of these, but sine of 90 is 1, okay? Great, okay? Now, here's the thing. Notice the sign, S-I-G-N, of these different torques. This one, the T sine 53 degrees times L, that one is positive. Why? Because this force wants to create a counterclockwise rotation. Imagine, right, if I have a pivot right here and I just have this force, that means the beam would start to twist that way. So that's why that's a positive torque. On the other hand, these two gravitational forces want to create rotation in the clockwise direction relative to the pivot, wouldn't they, if they were allowed to on their own? Okay, if this wasn't an equilibrium, thus they are negative torques. All right, so it's very important to get the signs right, and you got to imagine the object being free to rotate. At least that's the way that helps me. All right, so now we've done all the hard work, because setting up our three equations is the hardest part. Now, again, it's great that they're all equal to 0. That does save us a lot of trouble, okay? All right, so now at this point, we're just going to go ahead and solve for our unknowns. After all, we are solving for the magnitude of tension and for the reaction force, which means we want Rx and Ry. All right, so note this. This is an important thing. The pivot was chosen in order to make as many torque values 0 as possible. This is almost always a rule that we're going to follow, because I could have chosen any location as my pivot. I could have chosen the center of mass of the beam as the pivot. I could have chosen the end as the pivot. I could have chosen the location of the person as the pivot, or I could have chosen anywhere. And you could always get the solution, but you're going to save yourself algebraic hardship if you choose the pivot to make as many of the torques 0 as possible. And how so? How is that the case in this particular example? We'll take a look. By choosing the pivot to be right there at the black dot, right at the origin or the contact point between the beam and the wall, look what I did. I made both of the torques that would have been created by the reaction force, all right, I made them 0. Or maybe just the component of the reaction force that's perpendicular to the beam. But regardless, I made at least one torque 0. Because notice the reaction force does not show up in the torque equation. That's wonderful because think about it. That's one of our unknowns. And in fact, both r sub x and r sub y are both unknowns. And since they don't show up in the torque equation, that means we have one equation with one unknown, t, which means we can just solve for it directly without even doing any substitution or other algebraic tricks to solve for the unknown. How great is that? Okay? All right. So then we're just going to solve for t from our net torque equation. All right, just go ahead and just simply solve for it. Straightforward, 413 newtons. Now that we know t, we can plug it back into either of our net force equations and find the two components of r. So we find Rx from F net x, 249, and then we do the same thing for Ry, 570. Okay? It's as simple as that. Okay? So hopefully that makes sense. It's a good introduction to what a static equilibrium problem looks like, and honestly, dynamic equilibrium won't look that different. All right, let's do a few more. All right, so this one has more angles, more considerations, but same approach. All right, so here is all the forces. Since basically the figure showed, all the lengths, right? So it showed that there is, this thing hanging at the end of the beam, basically a big block that weighs 2,000 newtons, showed the angle that the beam makes with the ground, shows the angle that the cord makes with the beam, and so on. Everything we're going to concern about are the forces on the beam. We got the length of the beam and the fact that the cable is 3/4 the way up. So this shows all that. It shows one force, but it doesn't show any other forces. So all I've done here is just add the forces on top. I've also defined directions of positive y, positive x, and positive theta. Okay, and I know there's a lot going on, but look, I've chosen the pivot. The pivot's right here, which was a good choice because that way we have the two components of the hinge force, h here for hinge, which are not going to create any torques because they have a 0 length displacement vector. You can't have torque without length. Okay, we have the gravitational force right at the center of the beam. It's halfway up, so that would be a distance of 1/2 L, which didn't have really room to show in here, but it'd be 1/2 L. Then we have the location of the tension force, which clearly just runs along the cable itself. And then we have what I call the weight force, or force sub W. Okay? All right, and then let's just go right into, since we have all our forces identified, we've got our coordinate system set up, and we've even chosen our pivot, we're ready to proceed with writing the sum of forces and sum of torques. Right? Same approach every time. What are the forces in the x direction? Well, there's a hinge force in the x direction, this one right here, and there's a tension force in the x direction, and that's it. There's not many horizontal forces. In the y direction, again, more, okay? So there's a vertical component of the hinge force, that's basically like the normal force. All right, we have a vertical component of the tension force, right? Because the tension has both horizontal and vertical components. We've got gravity, which, a gravitational force of the beam itself, and then a gravitational force of this extra weight that's attached to the end. Okay, and obviously equal to 0 because there's no acceleration. And then we do torques. And again, it's torques, of course, about the pivot. All right, so notice this, right? Because this is the newest stuff. It's the stuff that is potentially the trickiest. So let's look at the tension force, okay? So the tension force is perpendicular, okay? How do we know the tension force is perpendicular? Well, we actually know because 25 plus 65 makes 90. So that's why we know that this is 90 degrees. It isn't necessarily so. I mean, obviously the cable could be at any angle, but we were given two angles that make it perpendicular, which is nice, okay? And so then we have our tension force times 3/4 L. All right, so this would be the full moment arm because the angle between the tension force and the displacement is 90 degrees, okay? All right, well, what about the gravitational force? Well, notice what I do here, all right? So I got the gravitational force, I've got the displacement 1/2 L. All right, the L's cancel out, which is why you see a line through all of them because each term has one. But I have a 1/2 L, that's the displacement. And then I've got cosine of 65. You might be like, wait, shouldn't I have sine of 65? After all, torque is force times R times sine of the angle between the two. Well, because this is not the angle between the two. Instead, this cosine is actually just taking a component of gravity, okay? So it's taking the the perpendicular component of gravity. And we can see that quite easily if we take a look at this gravitational force and we think, okay, well, this is 65 degrees. Okay, well, then cosine is going to be the angle that is going to make this, that is going to give me the component of the gravitational force that is actually perpendicular to the beam, right? Which would be this one right here. See? That's the cosine of 65. It's that component of the gravitational force, okay? Likewise, I'd want this component of the weight force at the end, okay? See? because those are the ones that actually are going to create, I guess it would be like this, okay? So these are the components that are actually perpendicular, okay? And that's why cosine of 65 gives me the correct angle, all right? Now, I could have thought of the angle between the displacement and the force, right? So I could think of a displacement vector like this, and then I could think of this as being the force vector, obviously is the force vector, and then I could think of this angle here. Well, that angle is just going to be 25. In that case, I take sine of 25. Well, sine of 25 and cosine of 65 are the same thing, aren't they? All right? So all I've done is just choose the one that I think is more intuitive, because in other words, I'm just taking the component of the gravitational force that is perpendicular to the beam. That's all I've done. All right? And I do the exact same thing with this 2,000 Newton force that's attached to the end of the beam. All right? And then those torques are equal to 0. The signs are just because the tension force wants to create a counterclockwise rotation, which is why it's positive, and then the two gravitational forces are negative because if allowed to, they would create clockwise rotation, which is the negative theta direction. Okay, negative angular displacement direction. All right, so there we have it, our sum of torques. And now it's algebra time. The first thing we're asked for is to find the tension in the cable. Okay, well, let's look here. Okay, did I choose a good pivot for making things go to 0? Yeah, because look, my pivot equation only has a single unknown. Yay, right? It's the same story. So I can solve directly for the tension force from my torque equation, and I get 1,465, and then I can just plug that back into my other two equations. All right, so then I plug it back in, okay, to find, let's see, what are the components of the reaction force? And that should say a B. But anyway, so this is the X component of the reaction force, 1330 newtons, okay? And again, that's by just using this equation. And then for the Y component of the reaction force, all right, a couple steps, and there it is, 780. Okay, so there we have it. There are all our forces. How did we find them? We found them by having our three equations: net forces in X, net forces in Y, and net torque. Notice we had three unknowns, because that's a big rule of mathematics, right? You can solve for as many unknowns as number of independent equations. With these type of equilibrium problems, we will often have three independent equations, thus we can solve for three values, all right? And they're often going to be forces that we're solving for, but sometimes it might be distances. All right, so I have another simple problem. This one we could have done in the previous chapter, but it definitely fits the bill of being having the look of a static equilibrium problem. A 240 Newton weight is hung from two ropes as shown. What is the tension force on the horizontal rope? What is the tension force of the horizontal rope? I guess in magnitude, okay, as a magnitude. So we're going to choose this as our pivot, okay, and then we're just going to consider the forces in the X direction, forces in the Y direction, and torque about the pivot. Well, here's the thing. I chose a pivot where all the forces are going to be applied, and thus there is no torque about that pivot. Okay. Now I could have, if I had chosen a different pivot, then I would have had to consider torques relative to that pivot. If I chose the pivot, it means there's actually zero torques. So then this just goes back to being a problem that is a free body diagram problem using Newton's second law in translation. And so then we can just go ahead and solve for our values. Okay. So there we go. Okay. All right, so now let's do our one dynamic equilibrium problem here. This is someone pushing a lamp across the ground. They want to push at a constant speed and they don't want it to tip. Because if it starts to tip, then it would be accelerating and it wouldn't be dynamic equilibrium. Instead, they want to push it at constant velocity, this person. Okay, so we got the mass of the lamp, 7.2 kilograms. We got the radius of the base, okay? And that's 12 centimeters, okay? That's this value right here. Okay, so it's got like a circular base, and so we care about its width essentially, okay? And then we have the height of the center of mass, that is going to be h, okay? And that would be, so if I was to include that in the figure, that would be right there, all right? And you can see I had added a typo, so I changed it to h, and it's 75 centimeters, 0.75 meters, okay? And they're pushing across the floor, which has a friction coefficient of 0.2, and how far below the center of mass of the lamp can the person push so the lamp slides at constant velocity without tipping? So this is a different type of question, right? This is not asking us to solve for a force. Instead, we have all the forces, and some directly, some indirectly, and instead we're solving for a distance. We're solving for x, and actually once we find x, then we're going to take h minus x to solve for this value there, okay? So that, because this smaller value would be h minus x, okay? Because we were asked for how far below the center of mass must the person push. Because the idea, of course, if they push at the center of mass, it will tip. If they push above the center of mass, then it would tip even more, right? If they push too low, then that's unnecessary. So we want to find that point of minimum distance from the center of mass where they can push without tipping, okay? But after all, the lamp here is just about to tip. So that makes for an interesting situation. Since it's just about to tip, but it hasn't started the tip, the actual forces of the normal force and the friction force are at the front edge of the base of the lamp. Let me zoom in on this a bit. So the forces act right there, and that matters, okay? Because if the forces were, say, lined up with the beam, right, if they're lined up with the center of mass, then the normal force would be in a different location, all right, which will affect the torques. But that'd be a case where that would be like static equilibrium. But since this is a dynamic equilibrium and we're concerned about the lamp tipping forward, the forces must be applied, that is the normal force and the friction force, must be applied at the front edge of the object that is in danger of tipping. And that's true of kind of this whole category of dynamic equilibrium types of problems. Okay? All right, and it is a common type of problem. Okay, so let's add our extra terms here. I call delta x, that's what we're actually trying to solve for. Here is the height, all right? And our choice of pivot, right there, the front edge. Why? Because that's going to make as many forces 0 as possible. So that checks out, right? All right, so here we have our dynamic equilibrium, same conditions, everything's equal to 0. Let's write out the forces. All right, so net forces in x, net forces in y. In the x direction, it's just going to be the pushing force minus the friction force. In the y direction, it's the normal force minus gravity. And then our torques about our choice of pivot, let's think here. We've got definitely the gravitational force is going to create a pivot. It would want to rotate it in what direction? It would actually want to rotate it in the counterclockwise direction. So the gravitational force creates a positive pivot. Make sure you can understand that. Imagine, right, if it was somehow nailed in there or like adhered to the floor, or maybe to the edge of something, and the floor just disappeared, then gravity would want to rotate it that way, wouldn't it? Okay? That's why it is a positive torque. Because again, positive displacement is defined, angular displacement is defined as counterclockwise. On the other hand, the pushing force, which wants to tip over the lamp this way, is a negative torque. Okay? And notice the distances. All right? So we only want the moment arm, which is just the component of the displacement that is perpendicular. Because if you think about it, the actual displacement from the pivot to the gravitational force would be that. That would be r. But we only care about r perpendicular. Okay? And r perpendicular is just the radius of the base, or 12 centimeters. Okay? And likewise, the displacement from the pivot to the actual location of applied external force from the person's hand would be this right here. That would be r. But we only care about r perpendicular, which would be this one right here. Okay? Now, why is r perpendicular vertical here, whereas it was horizontal for the gravitational force? Because the force is horizontal, thus the perpendicular must be horizontal. Must be, in this case, horizontal, or vertical, excuse me. And so then the moment arm is x. It's this right here. Okay? So that's the moment arm. Okay. All right. So now we are ready to solve for x and then quickly find delta x by using h. Because notice h doesn't show up, but we'll use that in our final step. All right, so we're going to find the pushing force from the forces, because we don't know the pushing force yet, but we know it has to be just enough to overcome friction. All right, so the pushing force must equal the friction force, and the friction force we know is going to be equal to mu k mg, because we know that from our sum of forces in the y direction. And this should look very similar to what we've seen in many types of free body diagrams. All right, so then we have the pushing force is just mu k mg, so it just must be 14.1 newtons. And that we can kind of think of that as the necessary pushing force for no translational acceleration, because we don't want the lamp to be slowing down or speeding up as it slides in the x direction. Okay? But then now we want our no change in theta. Okay? So then we want our torque equation to be satisfied, which means that's going to allow us to plug in our now numerically solved for pushing force into our torque equation and solve for x. When we do that, all right, so see, then it's going to be mg times the radius divided by the pushing force, plug in our numbers, and we get 0.6. Okay, so we found that x is 0.6. Now the height of the center of mass, or the vertical location of the center of mass above the ground was 75 centimeters. So that means we just take 0.75 minus 0.6, and there we go, 0.15. Okay, we've got our answer. All right, good. And that's actually not b. It's just there was only one part there. Okay, so question 1. This is the first concept question, okay? And this is an interesting one. The ladder below, okay, so it's a ladder. A ladder, by the way, is also one of those common types of static equilibrium problems, okay? And I do have one, it's a more complicated version of a ladder problem, but I'll show you as our last example. Okay, so here we have a ladder. It's leaning against the wall on Earth under the effects of Earth's gravitational field. I want to be very specific there. So for the ladder to not slip, is it necessary for the wall to have friction? You know, could this wall be like perfectly greased up or something and be totally friction-free? And could the ladder then still just rest there? Think about it. Maybe, you know, make sure, think if you have your own answer, okay? Could you imagine it staying there with that if this was totally greasy, totally frictionless? Well, yeah, because what could happen is the wall does not need friction, only the floor must have friction. Because look at the forces, right? So we got gravity. We can't, you know, that's the whole deal of being on Earth, right? Gravity is going to act, and it's going to act at the center of mass, always at the center of mass, by definition. And that means there has to be some force to oppose gravity. Well, that's the normal force of the floor, so that's good. And then there also, because of, turns out, electrostatic forces, you push on a wall pushes back. So clearly the top of the ladder is going to push on the wall. So there's a normal force from the wall. So we can't get away from this. This is just Newton's third law, and ultimately, you know, because of the nature of solids. Solids push back, okay? And if the wall pushes back, that means there needs to be some opposing horizontal force. Because we can't have only one force in the x direction. We have to have at least two forces in the x direction and two forces in the y direction. Well, we already got our two forces in the y direction. So we need a single force in the x direction. The friction force, but just from the floor, all right? We don't need a friction force from the wall because that would be redundant because we already have a normal force from the floor that's opposing gravity. We don't need a friction force in the wall. It won't slip if the wall is perfectly smooth, as long as there's enough friction from the floor, all right? So there we have it. We have net forces in x, net forces in x summing to 0, and net forces in y summing to 0. Okay, and then we could choose some pivot, and we could find that the net torque's also sum to 0. Maybe I could choose a pivot right there. Okay, all right. So let's look at the idea of equilibrium. All right. So with another concept question: 3 identical uniform rods are each acted on by 2 or more equal forces. So they're all the same magnitude, represented by the same length, all perpendicular to the rods. Draw the minimum number of force vectors on all 3 rods so that they are in static equilibrium. Give this a try. Make sure it's more effective. You try on your own, and then let me show you my answer. Okay, so in the first one, you actually would have to have a whole bunch of them because there's no way for it to balance out and not rotate unless you oppose all the forces, and you also have to make sure it doesn't accelerate up or down, right? So I don't want any net force in the y direction, and I don't want any net torque, and so this would be the necessary state here. Okay, all right. So again, remember it was just like that, but I had to balance these out because right now this would definitely rotate. It would rotate in this direction. All right, actually no, it wouldn't rotate in this direction. These ones would cancel out the rotation. But it would accelerate up, right? There would be a positive acceleration. So if I just add one here, then you might think, oh, well, then that's going to oppose the positive acceleration. But actually what's going to happen in that case is it's then, let's see, actually, no, we could get away with that, right? Because I could just add a force here, and then there'd be a balance in that direction, and we wouldn't have to worry about it. Okay, so we could actually do away with these two. We could just get away with just that vector. All right, so I was being overcautious because this would be enough for it to not accelerate in the y direction and not have a torque, okay? Because these two here, oh, no, I was right the first time. Because these two forces are actually both agreeing. They're both trying to create a counterclockwise, or actually a clockwise rotation, see? Both those forces are in agreement, so they don't cancel out, which means we actually do need these two as well in order to cancel out. So we actually need all 3, okay? All right, but look at these ones. These two forces are also in agreement. They both are kind of to act together in order to make a clockwise rotation. But since there's no force in the middle, we actually can just oppose them by just applying 2 more forces at the end. And there we go. We've got no acceleration because we have just as many forces up as down. And we've got no torque because we have just as much clockwise rotation as counterclockwise rotation. All right, or well, the other way around, but you get it, okay? All right, so now what about this one? All right, so this one's interesting because actually the best answer for this one is just to add another force right on top. All right, so if I just add an equal force right here, or you can think of doubling the length of this one, then it will balance out. Because these two forces here, they're already balancing each other in terms of torque. This one wants to create a clockwise rotation. This force wants to create a counterclockwise rotation. So they cancel out in terms of torque. This one doesn't create any torque because we can consider the pivot right there. All right. And so this one, and then in terms of translational acceleration, we only have to worry about having enough force that way so it doesn't accelerate up. So that's why I've just added another force on top that is equal length, right? So the pink vector is just on top of the pre-printed black vector. All right, so there's the idea of balancing out, Hopefully it illustrates some of the concepts behind these problems, so they're not just exercises in mathematics. All right, so final example, here's the big one, all right? I'll just kind of hit some key points, not go over every step. The ladder is leaned against the wall. The coefficient of static friction with the wall is mu SW, so S for or S for static, W for wall, and that's given as 0.3. The coefficient of static friction between the ladder and the floor is mu SF, F for floor, and that one's 0.4. The center of mass of the ladder is in the middle, so exactly halfway up. And what is the minimum angle that the ladder can form with the wall and not slip? Okay, so this one's interesting. It makes it particularly complicated that we have friction with both the wall and the floor. Typical problems like this would only have friction with one of the two and leave either the wall or the floor frictionless. Usually leave the wall frictionless, all right, for obvious reasons, okay? But here's the thing, is that's not the case here. And we don't need it to be the case. We can definitely solve this problem. It just requires kind of extra work, okay? So here's everything drawn out. I'm just clearly showing the components of our displacements. L here represents half the overall length of the ladder, and these are just the right triangles that I can form relative to the different points, okay? And then alpha is what I'm trying to solve for, okay? And then I'm just showing here that, there's my values of friction, all right? And the overall length of the ladder is just 2 times curly L, and here's just my coordinate system, okay? And all the force vectors are already shown. They're already printed on. Okay, so same approach, right? Start all of them the same, writing out the sum of forces and torques. All right, so sum of forces in X, sum of forces in Y. I'm using the summation notation here. All right, I meant to change that over, but same idea, just slightly different notation. And then I've got my sum of torques. But here's the thing. You probably thought, oh, well, I'm definitely going to choose either this point or this point because that will be the most forces going to 0. It actually turns out that that's a pain in the butt in this particular problem. This is the exception. So in this case, it's actually nice to choose the pivot point as the center of mass. And that way you have the torques from the normal forces and the friction. So we can think of the notation here. This is the torque from the normal force from the floor, which is F. And then this one here is the torque from the friction force from the floor, which is FF. So quick note on the notation here. FW is friction from the wall. W is normal force from the wall. F on its own is normal force from the floor. And FF is friction from the floor. Okay? The notation makes sense, but it's a bit clunky. Okay? All right, so then we have our torques. Notice that most of our torques are negative. Most of them want to create a counterclockwise notation, or counterclockwise, I should say, a clockwise rotation. So we look here, this one wants to create a clockwise rotation relative to my chosen pivot. This one wants to create a clockwise rotation as well. And let's see, the only one that wants to create a counterclockwise rotation is this one here, because all the other ones want to create a counterclockwise rotation, even the friction from the floor. See, because it would want to rotate it. It would want to rotate in the clockwise direction, which is the negative direction. See, this one also would be clockwise, this one would be clockwise, this one would be clockwise. So they're all negative, 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 negative. The only one that's counterclockwise, which is positive, is the normal force on the floor. See? Okay. All right. So then we just want to identify that because the forces in the x direction are quite simple, it tells us the normal force from the wall has to equal the friction force on the floor. So we have a direct relationship there. Then we want to think about each of the torques. I'll just kind of summarize them individually, see? So I'm just showing that we're just taking their components, just thinking about the component of the force that is perpendicular to the displacement, and that's all I've done here. I'll let you review that on your own. And then we go down and rewrite the sum of torque equation. All right, what I'm essentially going to do is I'm just going to express each of these just in terms of their definition of torque. And again, it's just using that torque is just F times R times sine of the angle between the two. That's all I've done. All right, and I've actually used sine in every one of them. All right, well, all but cosine because it was the component that made sense. All right, and the L cancels out. Remember, curly L is half the overall length of the rod. All right, or the ladder. Okay, and then we go on, and then we can rewrite the torque equation. It simplifies quite a bit. I move some things over to the right-hand side, which is why now it looks like this, not equal to 0 anymore, right, because I've just moved things around. Okay, and then I'm going to then take my sum of forces in the x direction and make a substitution. Okay. And then we'll go down and clean some things up more. Now I'm going to rewrite these two friction forces in terms of the definition of friction force, which is normal force times friction coefficient. Substitute those back in as well. Simplify. This green line is just showing that I'm going to make a final substitution, which I could have done earlier, to be honest. But here I substitute in that the friction force with the floor is just equal to the definition of the friction force. All right, which is and then. Oh, right. And then actually, this really is the step that I want to refer to, is that I know that the normal force from the wall is equal to the friction force from the floor, and I know that, of course, from the sum of forces in the x direction, which I also take note of up there. All right, so then then we're almost there. We're just then going to isolate our alpha because we've got a sine and a cosine, so I divide both sides by cosine over here. All right, divide that side by cosine as well. All right, so then it becomes a tangent of alpha. Take everything that was attached to this, the sine over to this side, which is why it ends up in the denominator, and then do an inverse tangent, and we get 48 degrees. All right, so yeah, the algebra was a bit there, but actually there wasn't too many hard angles or anything. If anything, it was just the interesting idea of making sure you're kind of tracking the 4 torques, all right, and making the unusual choice of the pivot. Because again, you can choose the pivot anywhere, but you'll set yourself up for a lot of hard algebra if you choose it at either of the ends. In this particular case, if this had been a ladder without friction force on the wall, again, a kind of a typical ladder problem like this, then the best choice for the pivot would have been the bottom, okay? All right, well, that's it. That's our introduction and a couple of really typical examples for static equilibrium, and we're going to see more about torque in later sections in this chapter. Well, thank you so much for watching this video.